Welcome. Today I tell you about the theory of relativity by Albert Einstein. Relax yourself and slow down. Let go your thoughts and listen to me. Don't try hard, just follow the flow. Focus on me and enjoy what humankind is able to do. The theory of relativity usually encompasses two interrelated theories by Albert Einstein: special relativity and general relativity, proposed and published in 1905 and 1915 respectively. Special relativity applies to all physical phenomena in the absence of gravity. General relativity explains the law of gravitation and its relation to other forces of nature. The theory transformed theoretical physics and astronomy during the 20th century, superseding a 200-year-old theory of mechanics created primarily by Isaac Newton. It introduced concepts including four-dimensional space-time as a unified entity of space and time, relativity of simultaneity, and length contraction. With relativity, cosmology and astrophysics predicted extraordinary astronomical phenomena such as neutron stars, black holes, and gravitational waves. By the 1920s, the physics community understood and accepted special relativity. It rapidly became a significant and necessary tool for theorists and experimentalists in the new fields of atomic physics, nuclear physics, and quantum mechanics. By comparison, general relativity did not appear to be as useful beyond making minor corrections to predictions of Newtonian gravitation theory. It seemed to offer little potential for experimental test, as most of its assertions were on an astronomical scale. Its mathematics seemed difficult and fully understandable only by a small number of people. Around 1960, general relativity became central to physics and astronomy. New mathematical techniques to apply to general relativity streamlined calculations and made its concepts more easily visualized. As astronomical phenomena were discovered, such as quasars, the 3 Kelvin microwave background radiation, pulsars, and the first black hole candidates, the theory explained their attributes, and measurement of them further confirmed the theory. Let's start with special relativity. Special relativity was originally proposed by Albert Einstein in a paper published on September 26, 1905 titled, "On the Electrodynamics of Moving Bodies." The incompatibility of Newtonian mechanics with Maxwell's equations of electromagnetism and, experimentally, the Michelson-Morley null result demonstrated that the historically hypothesized luminiferous ether did not exist. This led to Einstein's development of special relativity, which corrects mechanics to handle situations involving all motions and especially those at a speed close to that of light. Today, special relativity is proven to be the most accurate model of motion at any speed when gravitational and quantum effects are negligible. Even so, the Newtonian model is still valid as a simple and accurate approximation at low velocities. For example, everyday motions on Earth. The theory is based on two postulates. The first one explains that the laws of physics are invariant in all inertial frames of reference. The second one states that the speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. Until several years later, when Einstein developed general relativity, which introduced a curved space-time to incorporate gravity, the phrase special relativity was not used. The theory is special in that it only applies in the special case where the space-time is flat, that is, where the curvature of space-time is negligible. In order to correctly accommodate gravity, Einstein formulated general relativity in 1915. General relativity generalizes special relativity and refines Newton's law of universal gravitation, providing a unified description of gravity as a geometric property of space and time or four-dimensional space-time. In particular, the curvature of space-time is directly related to the energy and momentum of whatever matter and radiation are present. General relativity has a number of physical consequences. Let's get through some of them. Gravitational time dilation and frequency shift. Assuming that the equivalence principle holds, gravity influences the passage of time. Processes close to a massive body run more slowly when compared with processes taking place farther away. Light deflection and gravitational time delay. General relativity predicts that the path of light will follow the curvature of space-time as it passes near a star. Closely related to light deflection is the gravitational time delay, the phenomenon that light signals take longer to move through a gravitational field than they would in the absence of that field. And finally, gravitational waves. As objects with mass move around in space-time, the curvature changes to reflect the changed locations of those objects. In certain circumstances, accelerating objects generate changes in this curvature which propagate outwards at the speed of light in a wave-like manner. These propagating phenomena are known as gravitational waves. The theory of relativity made an impact in all sorts of cultural fields such as physics, of course, philosophy, psychology, and art. Some of these predictions have been confirmed by scientific experiments just a few years ago, and scientists are still trying to figure out further implications and implementations with other theories like quantum mechanics. But this is another story.